Hey everyone, my name is Favour Nerrise. I'm currently a AI and ML resident here at SandboxAQ. I specifically work in the quantum sensing department, focused on AQ That is our department that has to do with tools related to navigation and how we use different types of quantum inspired AI and other types of technologies to develop those solutions. I'm in my spare time. Part of why I'm a resident is because I'm also concurrently pursuing my PhD in electrical engineering at Stanford University. And it's been wonderful to be a part of Sandbox as I've been able to really merge all the different thoughts and skills that I've been able to get from my PhD into the amazing work that we do here at the company. And today I'm super excited to talk to you guys about what I've been working on the past few years. And it has to do with how we think about navigation in a different realm, especially in terms of digital sensing and all the cool tools we're using to do that. So, what is quantum sensing and why should you even care about it? Quantum sensing is basically a way that allows us to use these tiny little units called quantum sensors by utilizing properties of quantum mechanics that currently beat limits in sensor technology. So, a lot of sensor technologies are things you're already familiar with. For example, if you think about your smartphone, it has sensors on it like accelerometers and gyroscopes that basically allow you to figure out where you're moving, right? That's how you know to use your GPS when you're trying to use Google Maps or Apple Plans or the likes. But these are not so good all the time. And there are certain limitations that have to do with drift over a period of navigation, which we just can't allow for when we're thinking about real world system like airplanes and flight. So let's zoom in a little bit more into the work that we do with airborne applications currently within our AQNav division. So quantum navigation basically is enabled by this entire concept or field of magnetic anomaly navigation, MagNav for short. MagNav is an alternative to using GPS. Again, think about this like a digital compass. The way we do this is by using the Earth's magnetic field as a signal. What this basically means is that the Earth basically has these maps that we can map out, right? So you sort of see these signals on the screen where you have these variations over the Earth's magnetic map. And with these maps, they're anomaly fields, which basically means that there are signals that basically allow us to tell variations in those signal patterns. And based on those variations, you can actually basically leverage them and compute how that refers back to latitude, longitude, altitude, and other types of geophysical coordinates that we might be interested in for navigation. So why do we even care about using MagNav? GPS works amazing, right? Most of the world uses GPS. So why use something else? Well, if you're not aware, actually, GPS can be denied and is currently being increasingly denied in many types of use cases. If you're not familiar with how GPS works, there's a satellite constellation that basically exists just past the low Earth orbit system. And basically, that allows us to transmit all these signals. We receive these signals on Earth and emit them back, talking to those satellites. And the process of receiving and transmitting those signals, that means they're subject to human interference, right? That means jamming or spoofing can happen if somebody figures out what channels to basically block those signals. Or, for example, they could even modify the signals that are being sent or emitted from these satellites, which could be very, very dangerous, right? Especially if we think about sort of the natural use cases of these GPS signals. So we need something that is somehow resistant to any sort of human or environmental and atmospheric interference, and that is MagNav. So with quantum maps for navigation, we can basically have different types of sensors that basically enable a robust measurement system. So this means we can have scalar types of sensors, for example, using OPMs, optically pumped magnetometers. We can also have vector type sensors, for example, NV diamond sensors. And these basically allow us to have long-term stability, right? You can have these sensors located on your type of aircraft or whatever navigation system for years, up to decades. They're passive sensor measurements. So this means that you don't require sort of any active input, right, for the signals to be detected. And that means they're jam resistant. So humans can't, for example, figure out what channel and jam it because they are actually undetectable to those systems. And so makes it ideal for clandestine applications like we're talking about before. And also, again, quantum maps are very well known for having outstanding sensitivity, along with having a very small scaling form. And lastly, like we talked about, because we can combine different types of sensors for sensor fusion, this allows us to have vector level precision, which basically just means we have more faith and certainty in the exact measurements that we're having, especially when we have such tiny signals to collect. So how do we even get to MagNav? So MagNav has been explored for a very, very long time. This is actually not new. There have been explorations in MagNav specifically for airborne-based applications since the 50s or 60s by the military. And essentially, the entire approach for MagNav tends to be that if you have some defined system that you want to be able to measure navigation for, and you have some noise that is added into the system. In our use case, for example, think about having an aircraft, and then think about there being some additional noise like electrical measurements within the aircraft. If we're using MagNav, right, meaning we're using the magnetic anomaly signal or field of the Earth, which is located deep within the Earth with quantum sensors, that means we're able to detect not only just what the true magnetic core field is, but also that means we're also able to also determine what the aircraft noisy measurements are, like the electrical field signals. And we want to separate that because what we really care about is truly just the magnetic anomaly field that the aircraft is traveling, right? Based on what the ground truth level base measurements are. And we want to ignore everything else. And so the MagNav algorithm basically helps us define what state that system is from a mathematical standpoint. So you have these different elements that basically can be computed for within a MagNav dynamical system. And our goal is to be able to figure out how exactly do we identify different types of noises and how do we subtract that noises from the exact vector measurements that we want. So how do we do physics-informed machine learning for quantum navigation? So this has been a huge, amazing field that has been emerging rapidly the past couple of years. There was this amazing sort of use case or benchmark that was started by the MIT Media Lab in collaboration with the Air Force. And basically this challenge was called the Signal Enhancement for Magnetic Navigation Challenge Problem. And essentially what they wanted to do was that they collected a bunch of flights over Ontario in Canada, and they used a Cessna plane to do so. They had 1 hour flight time, about 200 kilometers of flight distance, and they did some figure-8 patterns with those flights. Again, think about maneuvers and how that affects the types of signals that you might see. On board this aircraft were 5 quantum magnetometers that were placed at different locations within the aircraft. And some things that they were able to find included things like noting that using these quantum magnetometers instead of just relying on GPS improved location accuracy by 4 times over INS alone. So another huge thing that we care about when it comes to MagNav is not just accuracy, but also really the certainty or confidence that we have in the error and the error range, right? So we think about reducing error to as little as possible. And this is because naturally location shows drift over a longer distance. So even with GPS, right, the truth of the distance and using GPS alone might slightly drift over time. And with alternative systems to GPS, we want to ensure that we're not increasing the error bound of the true signals, of the truth locations rather, that we're predicting or estimating. So my question for this specific paper that I worked on became, how do we capture complex, nonlinear spatiotemporal dynamics of airborne MagNav from a weak, noisy signal? So the backbone of this ended up being inspired by the entire concept of reservoir computing. Reservoir computing in computer science basically is being able to take a dynamical system like we learned about before when I showed you the MagNav algorithm, meaning we've defined that some system in nature, like magnetic navigation, has some existing behavior. And with that behavior, we can basically define these core attributes of that behavior and how those attributes interact with each other. And then we can make certain assumptions and then make certain predictions out of that system. So in this case, within our reservoir, where our attributes or elements are located, we use recurrent neural networks. They are deep learning models that basically allow you to have some temporal or memory-based information. And we fix them, however, with random recurrent layers. That is the reservoir. That basically means whatever patterns have been learned and the weights associated with that, we want to affix the learnings and then only train the weights that come out of the reservoir system. That way, we ensure that our physical assumptions about the observed dynamical system stays true throughout our entire predictions. And so this led to us using some recently discovered additional based networks called liquid time constant networks. And these were discovered by an amazing team that had come out of MIT Media Lab as well. And basically how LTCs work is that they use ordinary differential equations, which are mathematical and physical based algorithms, to basically solve super high dimensional, that just means we have a lot of data, sequential tasks, right? Meaning we have long context to our tasks. And what these do is that they're super adaptable. They also have typically reduced training because you have some prior assumptions baked into your ODE, your ODE problems that you define. They also have reduced requirements and they allow for more real-time processing because they're typically faster. And an interesting fun fact is that the pioneers of the LNNs, the liquid time constant networks, and many more, basically drew inspiration about these from an existing biological system, which is the microscopic nematode of C. elegans worm. The benefits of this tend to be very high speed, high efficiency, and again, potential for real-time applications where you want something super fast, sleek, and can estimate things with some mathematical certainty. And here's the architecture that we see for our liquid time constant network. So again, if you're given an input signal, which basically is some magnetic signals, some signals from an aircraft collected over time, including magnetometer signals, in addition to maybe other types of signals, then we feed that into an input layer of a neural network, which is basically where you have these units called neurons, and neurons take those signals and learn some patterns about them. We feed those learnings or patterns into our liquid or hidden layer. That's our reservoir. And in there, you have additional neurons that are called your hidden neurons or units. And those specifically focus on trying to learn associations between the different types of patterns that you've collected from your input signal. In LTCs, you can or you could not use an ODE solver. So if you use an ODE solver, that is not a closed form solution. If you don't use an ODE solver, it's a closed form solution. And what that just basically means is that we've predefined some physical assumptions about the hidden state of a neural network, and that allows us to basically have more bounds on exactly what we're computing when we estimate our output signal. And again, the output signal that we're predicting here is the magnetic anomaly signal, which basically just means we're able to have some certainty about what we hope the ground truth should be for the true aircraft magnetic anomaly signal. In the MagNav challenge, however, there's also another option for the ground truth signal, and that is actually a compensated signal from the magnetometer that is located within the tail stinger of the aircraft. And that's just basically because in that use case, the tail stinger of the aircraft is removed from all the noise of the actual main body of the aircraft. So you can trust that a compensated mag tail stinger signal basically is basically the most sure ground truth that you could possibly have for this use case. Something else to note about this hidden layer is you might note that there are different types of colors and or throughout this architecture, there are different colors of the units. So again, thinking back to the biological inspiration for this architecture, in our input layer, we consider those as sensory neurons. If you think about the human body, or if you even think about a worm, right? A worm navigates or travels basically by being able to sense things on the floor and its environment. So those sensory neurons are what collect input signals from its surroundings. And then you have these command neurons within the worm or within our architecture that basically sort of emit some commands, right? It tells the worm organs, right? Maybe to feel, send out feelers for this, or to maybe turn a certain way, to maybe retreat, or maybe to bunch up in a certain way. Those are the command or interneurons. So they're coming up with basically what possible decisions could be made and what probability to make those decisions. Then the motor neuron going to our output layer basically is what tells you exactly what action to take. So once you have decisions and the probabilities of those decisions within your command, then the motor neuron takes those with the highest probability and uses that to then make an action. For example, if I am a worm and I'm sensing maybe a hard object like a wall, then I might know to maybe climb up the wall. And the action I would take is to climb, meaning rotate my body to some angle and start climbing up the wall and or maybe to turn around. So like I mentioned before, you can either solve our LTC using a closed form solution or to not be closed form. In the closed form sense, we think about this as, again, we have some dynamical system with a bunch of parameters that we have for our MagNav phenomenon. And essentially with CFC, we sort of have this fixed liquid variable that we predefine with assumptions. So you don't have to actually solve for it in real time. And this allows the closed form solution to be more efficient and to have faster adaptive and causal times continuous time solutions without necessitating the ODE solver. And if you've used an ODE solver before, sometimes if you have lots of samples, like we see in our use case, where we have maybe samples collected every, zero point 0.1 second, then you can have hundreds of thousands of samples for a flight that is simply, less than an hour, or possibly if you have hours worth of flights, you might have up to, millions, even not billions of of samples that you might be working with. So you want basically computational solutions that are not only efficient, but also time efficient, right? And not just cost efficient. And so this led us to basically doing our experiment for the MagNav aeromagnetic compensation task based on the existing challenge I talked about before. So the data set we use is the open source data set that was released by the Air Force MIT Signal Enhancement MagNav Challenge. And essentially the goal here is to remove aircraft magnetic field from the total magnetic field that is being measured by our magnetometers, right? And this process is called aeromagnetic compensation. And by doing so, we basically derive a clean signal from MagNav that can be used to estimate our basically location coordinates and different types of measurements in real time. The various features that are collected by all of these different types of sensors, as you can notice here in this image, we have different types of magnetometers. Mag 1, that's the tail stinger like I talked about before, all the way at the back. Then you have these other magnetometers placed throughout different locations on the aircraft. And then you might notice that there are also other types of sensors, in this case, flux gate sensors, like flux B, flux A, flux CD. And these basically allow us to measure many other different types of things like positional, INS, and electrical measurements. So things like your temperature, which some of these existing sensors might not be temperature compensated already, meaning that you need to maybe remove those additional temperature effects and compensate for those for your clean signal. And so our findings using the LTC architecture, like I talked about before, basically ended up showing a 58% deduction in compensation error based on the RMSE root mean squared error metric. So how we did this was we took our TOS-Lawson, that is our baseline algorithm that is super good at doing compensation for MagNav. And basically we were able to see that on certain holdout flights that we had for the MagNav challenge, we saw some baseline errors that we cared about. And then we measured how our deep learning and AI and machine learning based models compared against all of these, against the baseline measures. And in our case, like we see, LTC performs better than existing traditional deep learning, and even more significantly so than the TOS-Lawson baseline. And specifically using the closed form solution, which basically means we're not using an ODE solver, we were able to see a 64% reduction in compensation error versus the classical TOS-Lawson baseline. And here is an example of basically a smoothened plot that we basically see of our truth signal against the predicted signal. So again, for the MagNav challenge, the ground truth signal in this case is not the magnetic anomaly field traditionally used, but it's actually the compensated magnetic signal from Mag 1 in the tail stinger. And in this case, using that measures the core field of the Earth, which is also ground truth signal. And we predict basically our signal using LTC CFC. And what you see here is a very close following, right, of our existing signal to some smoothing degree. So we apply some smoothing filters in this case to sort of filter out some of the noise variations effects that you might normally see. But again, we have some truth at why our error is so low is because there is a closer following of the original ground truth signal that we measured from Mag 1. And so in conclusion, what we see here is that we've been able to use a physics-informed model that basically models MagNav within this dynamical system. It employs some physical-based assumptions from leveraging physics-inspired neural networks. And this allows us to model higher-order nonlinear dynamics for aeromagnetic compensation. We also saw that we were able to offer magnetic effects corrections by leveraging existing concepts from TOS-Lawson. And we were able to embed this within LTCs with ODE solvers and also closed form assumptions to add some compensation correction for MagNav. And lastly, the truth of the low errors that we see allows us to conclude that we can effectively separate weak magnetic anomaly fields from noisy magnetic interference to have more accurate positional estimation in airborne magnetic navigation. And in looking towards the future, there are many ways in which we can improve this work. We think about, for example, SciML, which exactly is the field that basically tries to think about how do you embed more scientific-based assumptions like physics-based assumptions into your machine learning. In this case, we thought about the model complexity. Currently, why we chose to go closed form was because we noted that model complexity tended to be highly dependent on the choice of your ODE solvers, meaning you need a longer train or test time for these models if you have larger networks, especially over a larger number of samples like we tend to see in our use cases. We also thought about a challenge with how traditional models don't typically eliminate vanishing or exploding gradient problems, especially when dealing with long sequential context windows. And so this also led to more informed findings and outlooks on how we can better leverage geophysics-informed denoising, for example, leveraging other atmospheric conditions that might be corrected for prior to then using our pre-trained models on downstream tasks. And then even thinking about unsupervised learning and denoising. So can we perform compensation in contexts where we don't really predefine what features we should select or what patterns or physical phenomena to look for if we have a large amount of data collected from many different flights, many different maneuvers, with many different types of noise profiles? Could we use things like large quantitative models to then do some unsupervised learning and denoising to then use downstream estimations for other different types of tasks? And LQMs in general are a major type of technology that are coming out of SandboxAQ that we're super excited at leveraging in the future for the MagNav use case, among many others as well. And with that, I would say thank you to my wonderful team here at Sandbox and beyond, and to my wonderful advisors and collaborators as well at Stanford. Thank you so much.